Okay, we are on example 10.7, the speed of a pendulum. So this is just showing kind of what we've already been doing, but involving an angle. Okay, so this is stating that a pendulum is created by attaching one end of a 78 centimeter long string to the ceiling and tying a 150 gram steel ball to the other end. The ball is pulled back until the string is 60 degrees from the vertical. Then released. What's the speed of the ball at its lowest point? All right, so let's write this stuff down here. We've got the length of the string, which is 78 centimeters long, and there's a 150 gram steel ball that is attached to the other end. The ball is pulled back at 60 degrees. So let's say that we have, like, this is saying that it's attached to the ceiling, but let's just say that we have it on a ring stand. Okay, and that this length right here is 78 centimeters. And it says that this angle is 60 degrees from the vertical. So that's, from the ring stand here. All right, now, if we were just letting the string hang, it would probably come like right there, right? We need to figure out what distance this is at this point right here. Okay, so if we go ahead and do that, then we would take the length, which is 78 centimeters, which, by the way, you need to go ahead and convert to meters. So 0.78 meters. And since it is adjacent to the y-axis there, that degrees, you would do cosine 60, which would give you 0.39 meters. Okay, and whenever you go to find, it's wanting you to find the final velocity at that lowest point, so like right here. All right, so we found this distance here, and we need to figure out what the speed is going to be at that lowest point. So go ahead and do our energy equation again. Why did I put equals? That should be a plus. Okay, now think about this bob. If you've got a pendulum with a metal ball in the end, sometimes the metal ball is called a bob. All right, so at this point, before you've let go, does it have potential energy? Yes. What about kinetic energy? No. What about when it gets to this lowest point right here, does it have any potential energy? No, but it has all kinetic energy. So we have 1/2 mv squared is equal to mgy. Now, we're trying to find what the final velocity is at that point. So we've got velocity is equal to 2 times gravity times y. The masses cancel, and you end up with having to do the square root. So you do 2 times 9.8 times this 0.39 meters. Do the square root of that, and you should get that velocity to be about 2.8 meters per second. Okay? All right, so that's how you would do one if you involved an angle in there. All right, so you've got this quick check. A hockey puck is sliding on a smooth ice at 4 meters per second. It comes to a 1 meter high hill. Will it make it to the top? Okay, so let's think about that. We are trying to figure out if this velocity of 4 meters per second is going to make it to the top of this 1 meter high hill. Okay, so think about your energy conservation equation again. So you've got kinetic energy final plus potential energy final is equal to initial of both. So at first, here, the block's moving. Do we have initial kinetic energy? Yes. What about initial potential energy? No, we're on the ground. That puck is on the ground. So it has 0 potential energy. What about at the top? at the very top of this, and we're just wanting to know if it will make it up to the very top of that. So we'll say that it has no kinetic energy, but it would have potential energy then. Okay, so let's see. Mass times gravity times y is equal to 1/2 mv squared. Okay, so let's plug some of this stuff in. We are trying to figure out if this velocity right here will work. All right, so let's go ahead and solve for velocity then. So if we solve for velocity, it's the square root of 2 times gravity times y. So the square root of 2 times 9.8 times 1. And if you do that on your calculator with me, you should get 4.4 meters per second. So is that 4 meters per second going to make it? No, it is not. It barely does not, right? It'd probably make it pretty close and then it would slide back down. All right, so we've got energy diagrams. So potential energy is a function of position, we know that. And that functions of position are easy to represent as graphs. So whenever you do have to do the energy skate park simulation, this will hopefully, it'll be familiar. All right, so you've got this energy here, and it's telling you with this line, this sort of tannish line, that's the total energy. That's the kinetic plus the potential energy. This blue sloped line is showing you the potential energy, like the gravitational potential energy at its highest point right here is going to equal that total energy. Okay? And you can see even right here, this at the bottom point, that the kinetic energy is going to be highest. And so we'll show you like on a bar chart too how it relates on this one. So you've got 0 potential energy, so 0 potential right there, and 100% kinetic energy. All right, and as that potential energy slopes up, you can see that it's about halfway right here, halfway potential energy, halfway kinetic energy. All right, it goes to the very top. This should look familiar to a slide that we had pretty close to the beginning, but it didn't involve this second step where it had the slope on it. So just kind of see how it flows, on that sloped potential energy. Okay, this is showing you still potential energy, but now we're talking about springs and how it would look on a graph. And it doesn't make a slope, it makes a curve. Okay, it makes like a parabola. And basically, if you stretch that spring, in any way, then you've got like a left position versus a right position. And this is where it's at equilibrium, essentially. So where it's at equilibrium, it's going to be flying. If you pull a spring, like say, picture a slinky. If you pull it as far as you can without breaking the slinky, when it goes through that initial equilibrium state of it, it's going to be going super fast, okay? Like so fast you probably couldn't even see, like looking at a slinky. So at that point, you've got 100% kinetic energy. When you pull the spring back, you've got really high potential energy, and then it's going to flow like this, and it's going to go through the equilibrium position. It's going to go all the way stretched, and then it's going to start to come back down. And that curve is determined, that's what it's saying right here, by the spring constant. So just depending on how rigid it is going to determine what that curve looks like. And then here's another one that's showing you kind of what's happening. This is showing you that at these points right here, they're kind of at this like spot where they've basically stopped for a moment. So you've stretched it out. It goes through this equilibrium. It kind of goes back a little bit. It doesn't go all the way because, think about it. Unless you're on something that has absolutely no damping at all, you know, it's gonna give out a little bit, and then it's gonna go here, and then this is the maximum speed. So then it's gonna because it's gone so much more to that turning point there, then it's gonna go back up to that initial potential energy. And this is saying that from X2 to X3, it's slowing down, right? So as it's going right here, it's kind of slowing down. From X1 to X2, it's speeding up, and then it's going to slow down at X equals 3, and then at X equals 4, the particle reaches its maximum speed because that's at equilibrium, so it's going to be just flying through there. When the particle reaches X equals 5, it's going to turn around and reverse the motion all over again. Okay. Alrighty. So here we're looking at forces and potential energy, which we did kind of already in the in chapter 9. We can find potential energy by calculating the work, right? So the force times a distance. And if we know the system's potential energy, then we can find the force, essentially, if we can figure out what the displacement is. So the force of whatever is going to equal the negative potential energy divided by the displacement. Okay, so and they're showing you here on another graphical image of what's happening as the displacement approaches 0. You can find that the force is at this position S right here. So the force is the negative of the slope of the potential energy curve. Okay, so the negative of whatever that slope is. All right, and we've got another graphical situation. This is showing you figure A, that the potential energy curve for, this is a spring, remember, and then the force on an object attached to the spring, you can find by, you would do the negative of the slope. Okay, so this right here, the negative of that slope of the potential energy curve. All right, so figure B is just showing you what the force versus the X graphical situation of this slope would be. Okay. And another, which is showing you if you have a potential energy versus displacement graph and you've got a negative slope, then it would, on a force versus displacement, would be this constant positive force because it's the opposite of. And then as a 0 slope, it would just kind of go down from 2 to 3 here and be like 0. And then as it has a positive slope back up, it's going to be the negative of that. So a negative of whatever that would equal out. You don't have any numbers on the y-axis, so you can't find that. But anyway, it would be represented similar to this. Okay, we're almost actually getting close to being done, I believe. I'm a little concerned about my time on this video, so I'm going to stop it here, and then I'm going to start on another one.